This is video 231, and our objective in this video is to be able to describe the beginning and end behavior of a polynomial and to factor to find the zeros. So we're just going to break it down and start with those simple pieces. So let's take a look at reminding what the definition is. This is the definition that your book will give. This definition says a sub n x to the power n, a sub n minus 1, x to the power n minus 1. The thing is, they're worried they're going to run out of letters, so they talk about these a sub n's, a sub n minus 1. Those are the coefficients. So they're integers like 6 or negative 2. They're numbers. They could even be fractions, 1/4, 1/2. They're any real number. Now, x to the power n, remember we talked about in class, has to be a whole number. You can't have a fraction or a negative power with the x values. So this could be x to the 7th minus 2x to the 6th plus 8x squared minus 4. So some of your x values could be non-existent because you could have a 0 for the a sub n value in that case. But this is a polynomial of the 7th degree. And that's the next terminology that you'll see me using on occasion, as well as the book. This is the degree of the polynomial because it is the highest power in the polynomial of x. So x to the 7th tells me that the degree is 7. So it's not about the number that comes first, it's about the highest x power. If I add on 8x to the 10th, now I have a degree of 10. Okay? So the degree is the highest x power in your polynomial. So a couple of reminders about the graphs. We'll be graphing in the next video, but to remember what the graphs look like, we want to make sure we have smooth rounded corners like it's described here. We never want to connect them with jagged edges like you see here. So when you graph your functions, you just want to connect the points that you're going to find with a nice smooth curve. You'll never have discontinuous jumps in the graph either, like you see down here. We defined it today as a function, so it won't have those breaks. It will have only one input for every output. In fact, the one that you see down here is in fact a function. It's just got a break in it, and ours will never have a break in a polynomial. So now, here's our next goal. We're trying to determine the end behavior of a polynomial. So there are 2 steps to do this, but first let's take a look at these 4 pictures. These are 4 scenarios that could happen. Okay, these 2 scenarios at the top are similar in that they start coming from one direction and they end going in the other direction. So this one starts falling down to the left and then it ends rising. Okay? The same thing goes for this one, but it's the opposite. It's actually starting rising and then it ends falling. So those 2 are similar in that they start and end going in opposite direction. The 2 in the bottom down here are similar in that they start and end going in the same direction. So these both end, this ends upward, starts going upward, it ends going upward, and same thing with this one, but it is going downward. So that is talking about the end and beginning behavior. That's how these 2 are going to be similar. So these 2 are going to be linked as well as these, and hopefully you're remembering some of this from the past, from your previous classes. So let's talk about how we're going to determine this end behavior. Step 1, you have to ask yourself, is it an even or odd degree polynomial? So remember, the degree is the highest power in the function. So in this function, the degree is 3. So therefore, it's an odd degree polynomial. In this one, the degree is also odd. The degree is 21. But you're looking for the degree in order to decide, number 1, is it odd or even? Then we'll decide what direction it's going to be going. So, if it's odd, that means you're going to start and end pointing in opposite directions. So these 2 graphs are good ones to take into your notes. These would be graphs of odd degree polynomials. X to the 3rd, x to the 5th, x to the 21st, x to the 99th. Anything odd will have a characteristic that it will start and end in opposite directions. Now, how do we decide if it is going up or down and it ends going up, or if it ends going down like the second one? Well, that will depend on the coefficient of the leading term. And they call this the leading coefficient test. So we look at the leading coefficient of the highest degree. In this case, the leading coefficient is 1. So it's a positive. It's got a positive leading coefficient. So that means that my odd function will end going up. This is when it has an odd degree, it will end going up. So this graph is going to start going down and end going up. Okay, the number of turns in there will depend on the zeros that exist and what we see in that. So we'll be waiting on depicting the number of turns based on the number of zeros. So that will come later, but we know it's going to have a general form like this: start down, end up. And the 21 degree is going to have the opposite effect. It's going to end going down if it's negative. So this one's going to start being up and end going down. It's going to fall at the end. So this should fit with everything else that you know about quadratics and such. Now, even ones are similar, but these are the ones that start and end pointing in the same direction. So they're the bottom graphs on your screen. And these ones will be similar to your quadratics because we already work with x squared, and we know x squared looks like this if it's positive or this if it's negative. Now when we work with x to the fourth and beyond, the positive will end and start going up. Negative will end and start going down. Okay, so they may not be as symmetrical as the ones that I drew, but they will be ending and starting in those directions. So for instance, this could be a quartic, a negative quartic. It has a value that starts going down and it ends going down. So those are some important notes to jot down and or think about and have in your notes so you can answer the questions that you'll see in your checkpoints. So let's talk about finding those zeros. So when we're trying to find zeros, remember zeros are the same thing as the roots, the solutions, or the x-intercepts of a function. We're basically asking when is this going to be 0? So in order to do that, we actually have to factor. So we're going to get out our factoring brains, and we're going to figure out a way to factor this. Now, when it gets to be cubic, it's in quartic, it's going to be a little bit more challenging to factor. Okay? A couple of ideas to help you along. You always want to look at your final constant term because you know that's going to be affected. Now, in this case, -3, there's only a couple ways to multiply to -3. It could be -3 and 1. That would give me -3 in the bottom corner. Okay? We're not going to officially solve it this way, but we're going to think that through because we know that we have to get that -3 at the end. Okay, we also know that this coefficient is 1. So I'm going to make a guess that x minus 3 is a factor of this polynomial. So I'm going to guess that x minus 3 times something will give me the polynomial that I'm working with. So the way I guess, remember, is I start to fill in stuff I know. So we've done a little bit of this already this year. We put in x third. The only way to get x to the third is if x squared is up here. But then now that affects my bottom term. So that has to be -3x if -3x squared if my -3 is in fact one of my factors. So let's take a look now at what we have. We have a -3x squared down there, but we really want positive 3x squared. So in order to get that, I'm going to want a 6x squared right here. So that means this has to be plus 6x. But once again, that affects this bottom term here. So this has to be -18x. So I look back to my problem and I say, well, shoot, I don't want -18x's. I only want negative x's. One negative x. So this somehow has to be 17x. So that means this has to be 17. Well, this is not going to work because I really wanted that to be 1 so I could get -3 in that corner. So -3 times 17, I'm not even going to bother with that. It's 41 negative, but that's not helping me because it is not a factor because I did not end up with -3. So I start all over. It's good to do this with pencil and or slightly in your head, lightly written on your paper. So x minus 3 is not a factor, so now I'm going to test x plus 3. So I'm going to erase what I started, and I'm going to test x plus 3. X plus 3. So that means this would be 3x squared. 3x squared is actually what I want here, so that looks promising. So that means that I already have the first two terms done, so I don't need to worry about my x squared. So now we look at my x term. So this is taken care of, this is taken care of, now I look here. The only way to get negative x is to have x times negative 1. So negative x goes there, and take a look, negative 1 times 3, negative 3. I've successfully factored the polynomial. So x plus 3 times x squared minus 1. This product will give me that sum. So I've successfully factored. Remember, that helps me see my zeros because I'll use my zero product property. But before I continue, I want to see if I can factor this further. So I always start with polynomials, factoring them with a first degree binomial here that you see here. And then I look to the higher degree one, the squared in this case, to see if I can factor it further. Hopefully you recognize this is one of our special products. This can be factored into x minus 1 times x plus 1. Then I am officially done with this factoring. Now I can finish solving by using my zero product property. And I can ask, when is x plus 3 equal to 0? When is x minus 1 equal to 0? And when is x plus 1 equal to 0? And I can find my three zeros. My three zeros are negative 3, 1, and negative 1. Those are my three zeros, my three solutions, my three roots, my three x-intercepts for the original function. Now we're going to try it again, give it a shot, and then you'll try some on your own. So once again, we have x to the third, 5x squared minus 9x minus 45. So we're going to start again with making a guess and then seeing if it works. So I'm going to try again. Let's see, I think of ways to get 45 because this number times this number will give me 45. So 9 times 5, 3 times 15. Sometimes it's good to start with your smaller numbers like 3 just because it might keep things smaller and work. So I'm going to try a negative 3 again. We'll see if this one works this time. So once again, I start by filling in the first term. X to the third would have to appear right away. That would give me negative 3x squared down here. Once again, I don't want negative 3x squared. I want 5x's. So I put in here what I would want to make 5x's. So this has to be 8x squared in order to add to 5x's. So that means this has to be a positive 8. So then, positive 8x, excuse me. So then now I fill in the bottom slide here, 8 times negative 3, so negative 24x. Once again, I don't want negative 24x. I only want negative 9x's. So negative 24 and negative 9. So this must have been positive 15x's because those two would add to negative 9x. So I take a look here. How would I get 15? Well, it would have to be x times 15. And then take a look. It's going to work. 3 times 15 is 45, negative 45. So I've got all three of my different pieces here, all four of them filled into my generic rectangle, so I've successfully factored. So my factors so far are x minus 3 times x squared, 8x, 15. Okay, this one's done, but now I need to look at this one and see if I can factor it further. Hopefully you get a little bit quicker at this, but this factors to x plus 3, x plus 5. And once I have my two factors, I can see my three solutions. X equals 3, negative 3, or negative 5. Those are your three zeros, roots, solutions to this cubic function. So remember, factoring, it just takes a guess and then you check it. We're going to learn some strategies to quicken this strategy, especially when you're trying to find these zeros a lot quicker. So let's take a look at your checkpoints. Give these problems a shot. Try to factor these. One hint I have for you is always to look for a common factor. So is there something that goes into all of these? Or is there something that goes into both of these that you can factor out right away? Bring in your questions to class and we'll go over them on Monday.